on the, I'm going to bring it on the slideshow mode. There you go.
Perfect.
So it should show up there. Great. It's again wonderful to be here. Thanks for the introduction, Michelle. I'd rather be there in person, but I'm in Hawaii. No, I'm just kidding. That's just my background. My background is in Hawaii, but it's great to be here on online on webinar form. So we are both Joe and I are going to give this presentation. Joe is working as a postdoc here with University of Delaware with us. So the plan is that I'll give a talk for about 25 minutes, and then Joe will pick up the latter half and go for about 15 minutes or so. That's the plan, and try to wrap things up in 45 minutes, 45 minutes. Okay, so like this slide shows, I'm going to highlight some of the aspects about soil health, how we can enhance soil health in our stream and floodplain restorations. So before I get into the details, let me thank all the funding programs, the EPA wetland program that funded one of our grants, the Chesapeake Bay Trust, where we have 2 grants looking at stream restoration aspects, and the USDA NIFA Soil Health Program. Let me also recognize many of our colleagues who have contributed to this work and students. Dr. Sujay Kaushal at Maryland, Dr. Jinjun Kan and Mark Pipok at Stroudwater Research Center, Brian Tetrick, restoration practitioner at WSP, Larry Trout at Strogan Environmental, Dennis Janito and Richard Rowland at Baltimore County, Dr. Erin Peck, who's at URI, and many UD colleagues, Dr. Harsh Bias, Alexis Yakulak, Visesh Joshi, Matt Sena, and Dr. Moklesu Rahman. So all of these guys have tremendously contributed to our research, and the work that I'm presenting is really a combined effort of all of these contributions. So the presentation that I'm making today is kind of builds on this work, this paper that we wrote last year, More Than Dirt, Soil Health Needs to be Emphasized in Floodplain Restoration. And it provides, this paper is available for free from that link from the Journal of Soil Systems, and it provides an initial blueprint, some of our initial ideas on how soil health can be addressed in stream and floodplain restorations. And this is an excellent example of a partnership between academia, industry, and the government. And as shown by the co-authors over here, that span all 3 of these different categories. And what we're doing now is trying to test some of the ideas and hypotheses that we presented in this paper using specific sites and data that we are collecting, which part of which we're going to present in this presentation. Okay, and most of you guys know about this. What are stream restorations? What are stream and floodplain restorations? I'm essentially preaching to the choir here. Essentially these restorations reconnect floodplains and terraces that have been disconnected because of accumulation of legacy sediments, inside streams, and so on and so forth. The key objectives, again, many of you may be aware of this, is essentially to reduce erosion, mitigate sediment pollution, enhance hydrologic connectivity of the stream and the floodplain, promote natural nutrient removal processes like denitrification through that flooding and variable oxic and anoxic conditions, and also to enhance riparian vegetation and habitat. This is an example of how a stream restoration would work. You have the nitrates in the waters that flood the floodplain. The floodplain provides the environment for denitrification, and you remove the nitrate out of the stream waters. So, these restorations have been performed by various approaches. And again, many of you may be familiar with this. One of them is natural channel design. where you provide the appropriate meanders, the pools and riffles, and I won't get into the specific details, but this is one approach. The other one is regenerative stormwater conveyance, where you provide the weirs and try to slow down the velocity of flow in the stream, enhance the residence time, increase the organic matter, again, to facilitate the biogeochemical processes that may remove nutrients like nitrogen and phosphorus out of the streams. The third approach is a third or fourth approach would be the legacy sediment removal and stage 0 type of restoration, where you excavate the sediment out and reconnect the floodplain with its original landscape, original floodplain, which would have been there before the accumulation of legacy sediments. And what I mean is, we are trying to get to this situation where we are trying to reconnect or recreate the floodplains or the valley bottom conditions that would have been present before. We are certainly not going to reach those ideal conditions, but that's what we are trying to do here by removing the legacy sediment and trying to recover those buried wetland soils and try to establish those type of ecosystem services and conditions. And you all know, you're well aware that the stream restoration is a growing industry. It's a $1 billion industry across the US. It's extremely popular in the Mid-Atlantic and the Chesapeake Bay. The number of permits and the length of the restoration is increasing. And the cost could vary anywhere from $1,600 to $4,000 per meter of restored length. And again, that depends on the type of design and the level of complexity involved. And so these restorations are providing great value. It's an important tool to mitigate nutrient pollution, meet some of the regulatory goals in reducing sediment, nitrogen, phosphorus, and water quality, meet some of the TMDR goals. It has provided important gains in erosion control and water quality improvement. There's also, the intent is also to provide ecological uplift, enhance riparian and stream habitat, and the associated biological conditions. However, we have gained a lot by these stream and floodplain restorations, but there are also important challenges and questions that still persist, which we should be addressing. We all know that there's limited monitoring of these systems, not to the extent we would like to have. And there are a lot of questions about the long-term effectiveness of these stream and floodplain restorations. How long does that effectiveness persist, and how soon do we get those returns in terms of water quality improvement, on ecological uplift, so on and so forth. There has been a greater focus on the channel form and geomorphology in many of these restorations. There is limited attainment of functional and ecological uplift, and the ecosystem services that are provided. Again, many of you may be aware of the controversy and the concerns involved with tree removal, especially when you're removing mature trees, and the trade-offs associated with removing legacy sediments. That's a tremendous concern in the public in terms of removing mature trees when doing these floodplain restorations. And also the issues about encroachment and of invasive species, invasive plants, non-native plants on the floodplains. So we do have to address these public concerns and these issues. And press coverage like this, which again, many of you must have seen, does not help the cause. So we do want to address these issues. So what we feel is we certainly need to address those challenges, those questions, but we believe that not addressing soil health on the floodplain could also be contributing to some of these problems, these questions. And we need to address soil health on the floodplain as well as in the stream, um, to better to have a better restoration overall, and achieve those ecological goals. So what do we mean by soil health? Essentially, soil health could be defined as the soil physical, chemical, and biological properties that enhance those important ecosystem services like infiltration, runoff infiltration, erosion control, nutrient removal through biogeochemical processes like denitrification that removes nitrate. If you have good, healthy soils, that's also going to contribute towards plant growth and its resilience, and certainly provide an excellent habitat for microbes and other insect biota. So those are the various aspects that we want to enhance, and that's what we'll be talking about in this presentation. So why haven't we done this before? Why haven't we addressed soil health already in our restorations? And there are multiple reasons, and some of them are listed here. There's a lack of knowledge about soil health and its important consequences. We don't know as much. Most importantly, there's an absence of specific design and implementation best practices, and the unavailability of specific soil metrics and tests. So what are the soil metrics that we go after? What are the metrics that we can use to establish a successful floodplain restoration? What are the metrics that we monitor over the long term to see how things are changing? So those metrics are missing in many of our design practices. We don't know what should we be shooting for? What is the ideal soil condition that we should be going after? Rather than perfect or ideal, I should say desired, really, because sometimes those perfect or ideal conditions may not be attainable. And then finally, there's a lack of regulatory credits or benefits that the restoration agencies can receive for doing the soil health. And I think that needs to be changed. That needs to change if we are really to make sure that soil health works in our restorations. So that paper that I mentioned before, our blueprint, kind of provides initial guidance on some of these issues, but we're going to emphasize that in this presentation. So what are the challenges that we see in terms of soil health when we do these restorations, where the focus is on the stream and not as much on the floodplain beside it? What we see is, and this is through personal experience, where we have gone out on some of these sites to auger and take soil samples, and we could barely auger through that floodplain. It was so hard. It was extremely compacted. Because of the heavy equipment that was used to excavate the sediments or redistribute the sediments. So the floodplains and the soils are extremely compacted with low porosity, which is not good. The floodplain soil thickness is reduced, and that translates into lowered in water infiltration. So if your soils are compacted, you're going to lose that ecosystem service of runoff infiltration. As the stream floods, it won't be able to accept that much water. The floodplain won't be able to infiltrate that much water if your soils are compacted. So these are some of the physical impacts. There could be many others. Here's some of the geochemical impacts, which I've mentioned in the paper. In doing these restorations, we tend to homogenize our floodplains. We are providing either very little organic matter or it's uniformly distributed. So we are losing that heterogeneous surface on the floodplain. We are losing the hotspots, and I might talk about that later. We are losing some of those buried relic organic layers because we are not considering those in the design process. Again, I'll get to that in a bit. In doing so, we alter the biogeochemical processes. If we don't have good soil health, if we don't have enough organic matter and its spatial distribution, we're going to lose some of those nutrient removal services like denitrification or phosphorus sorption, so on and so forth. And on top of that, if we are adding other soil conditioners to the floodplain during restoration, or other soil amendments, which may have some contaminants, that could increase the leaching. So that's a few of those biogeochemical aspects. Here's the biological aspects, and again, a few of them. If your soils are compacted, if your floodplain is compacted, it's not going to be able to hold those tree roots very well. It's going to generate a lot of runoff. Those runoff velocities are going to be high. And this is what we have seen. A picture I took on one of our restored sites where the trees, just the saplings that were planted, just couldn't hold in that highly compacted soil. So you could see these root ball craters or root ball potholes when a big storm comes and just displaces those saplings or those small trees that you have planted. It could also strip out the fabric that you have placed on the floodplain. By excavating the legacy sediments, by redistributing the soils, we are also losing the microbes and the mycorrhizal fungi that was there. And that is, we recognize that's part of the restoration process, but we want to make sure that the recovery happens quickly. And the way we do that is to provide better soil health. And like I mentioned before, we, in many situations, I mean, many of these restorations, they're not considering the pre-colonial organic horizon, the pre-colonial floodplain that was there, and the remnants are still there. You can see the organic horizons on the stream banks, and it'll be clear in the next slide. I refer to them as living fossils of the landscape, and this is what I'm talking about. You see the dark layer there. It was at one of our sites, and we actually carbon dated that hydric organic horizon. And it was the carbon date age came to about 1,000 years old. So, and this floodplain restoration happened at this site, and unfortunately, that organic layer wasn't considered as a part of the design. Again, because again, not blaming the designers here, but it just wasn't part of the design process here. But going forward, we need to make those changes. And these hydric soils, these buried organic hydric soils, buried below the light-colored legacy sediments, are extremely important. They may contain that original microbiome, as well as they might contain seeds of plants that grew hundreds of years back, and which some of these seeds and microbiome are still viable. Folks have done measurements and tests, and they have seen that, yeah, some of the seeds are viable. So what I'm trying to get at is, by leveraging this historic microbiome and those seeds, we may be able to rewild our landscapes, our current landscapes, which are really getting impacted or hit by anthropogenic activities. So we need to do that. We need to leverage these hydric soils. And there are restorations that do so. Here's an excellent example of a very successful restoration, which used the stage 0 type of restoration in Pennsylvania, in Lancaster County, the Big Spring Run restoration, where they removed the overlying legacy sediments, which you can see in the top photo. They removed that legacy sediment, but let the organic layer, the pre-colonial hydric soil, the dark colored organic layer, be there. They left it as is in the restoration picture below. And that actually, there were viable seeds in there, and they came out. Those plants sprouted. And slowly the microbes that were there hundreds and thousands of years back will also recover and populate this restored landscape. So this is the ideal condition. This is how we can really leverage our historic diversity, soil diversity, and soil health. Just to highlight again, the value of these microbiomes, their diversity. The diversity could be way more than the modern topsoils that are getting affected by pesticides, PFAS now, other contaminants that we are applying. There could be novel microbes there, which could provide really valuable ecosystem services. Here's one example of one of my colleagues, Dr. Harsh Bias, in our plant and soil sciences department. He's taking these historic soils, identifying specific microbes in there, and leveraging these microbes for plant growth as a biofertilizer. So look at this photo at the bottom, where you can see the control on the extreme right that didn't receive those microbes from the historic hydric soils. That plant is pretty pathetic, small, shriveled up. But the other plants on the left here from, what is it? I think I can barely see the letters there, but going from left to right, the microbial inoculation increased. So as we provided greater amount of that specific microbe to the plants, it enhanced the plant growth by leveraging by essentially increasing the nitrogen fixation and making it available to the plant. And remember, these microbes were there hundreds and thousands of years back when we were not fertilizing our landscapes. So they had evolved in a landscape which was nutrient deficient, nitrogen deficient, and they were trained, those microbes were trained to leverage nitrogen from the air through nitrogen fixation and provide it to the plants. That's what they're doing it right here in this picture at the bottom. And that this is just one example. There could be other amazing things in these buried hydric soils. So what we are trying to do is we're trying to, in our current research, which as we'll highlight as we go through this presentation, we'll highlight, we are identifying some of the sensitive and robust soil metrics to characterize the physical, chemical, and biological soil health. We are also assessing the use of hydric soils, historic hydric soils, and how do they recover? Do they recover immediately? Are there microbes dormant? What types of microbes there are? So on and so forth. We are also trying to develop what are the best construction? What are the best construction practices we can recommend for enhancing soil health? And then we are also evaluating some of the soil metrics to test the long-term effectiveness of restored floodplains for different processes like denitrification. So here are some of the soil metrics that we suggested in our paper and which we are testing now. Again, the intent here is to provide or recommend or suggest soil metrics which can be easily tested, have specific, provide specific ecosystem services, have specific end products, and which are also cheap in terms of analyzing and getting them analyzed through a commercial lab. So these are some of the initial metrics that we suggested in that paper and which we are actually evaluating in our research here, which Joe is going to be talking about in a bit. We talked about, we're looking at bulk density as a measure for compaction, soil texture, looking at the sand, silt, and clay contents, because that will affect a whole bunch of soil properties. We're going to look at soil aggregate stability, which does change post restoration with time, as you have greater biota in the soil, like earthworms, and their excretions can change the aggregate stability. Obviously, pH and organic matter are one of the most important chemical parameters that can drive various chemical processes. Electric conductivity, total carbon and nitrogen, which could be important players in denitrification and other soil health processes. And also aspects like, in terms of biological soil properties, looking at phospholipid fatty acids. So the PLFAs can characterize the microbial biomass in the soil, and especially the live microbial biomass, which could be a very good test to assess soil health. Are the microbes growing? What is the current state? How do they change post restoration, 3 years, 5 years, 10 years, 15 years, so on and so forth. And there are better metrics, more specific metrics for characterizing microbial diversity, microbial biomass. We have functional genes and high throughput sequencing you could do. But those are also more expensive and also need more expert evaluations. So again, our idea, our intent here is to provide metrics that restoration practitioners could implement easily without going after really detailed experts or experts in those fields. So here are some results, like I mentioned about the recovery of the hydric soil in the floodplain and how quickly does it recover. So we kind of hypothesize that, hey, those microbes in that historic hydric soil, which is buried under feet of legacy sediments, which is disconnected from the surface, disconnected from the live microbial or live organic matter that is coming from the plants and the trees, most likely those microbes will be dormant. And that's what we have found in this research, and which is published here, which the article is shown here. It was published in Restoration Ecology. You can see in this paper that essentially those microbes are dormant. They have very low denitrification rates, but we still recommend that, hey, those hydric soils should be retained as is because they do have the microbes, and their diversity is high. Those microbes may take some time to recover and provide those ecosystem services, and it could be 3 years, it could be 5 years or more. But we still need to do that, and we need to consider this delay in our ecosystem restoration recovery. In that, hey, we won't get denitrification at its maximum potential right away. It's going to take time. You have to balance this recovery or this delay in terms of your TMDL goals. So yeah, so we need to consider that. And here's a plot kind of quickly showing some of the results that we found. Again, all of this is described in greater detail in the paper. But just to quickly show you, the historic values are on the right. The modern wetlands soil values are on the left. Pre and post restoration, we buried both of these soils on a restored floodplain and saw how things change after 1 year. So this was just a 1 year. But what the interesting aspect of this paper was, we compared these historic soils across 4 different states: Delaware, Maryland, Pennsylvania, and North Carolina. So we got 13 soils from historic soils from these different states and compared their denitrification rates, their total microbial biomass, their bacterial biomass, their NOS-G functional genes. And across most of these soils, all 12 or 13 soils, we found that the historic soils were performing lower, as we expected, at the initial phase of the restoration. But here's another study, which Alexis Yakulat is doing, a PhD student here at UD. And what she has a 3-year time frame or data set. And what she's finding is that the denitrification rate of that historic soil, which is the red box here, will increase, will recover. Here you can see by the year 3, by 3rd year, it's jumping up and starting to catch up with the wetland soil denitrification rate, the modern wetlands. And remember, this is again a very limited perspective here, just the denitrification rate. We are not looking at the full microbial diversity, which could be in the historic soils, could be much higher. But we want to test that out. So some of these, again, we want to lay out some of these practices in best management or best construction practices for soil health. So what we should be doing in some of our restorations, we should be providing sufficient floodplain soil thickness. We should be avoiding some of the floodplain compaction and disturbance, especially by that heavy equipment, which and ideally should be limited to the stream. And especially if the stream bottom is gravel, heavy equipment could, the stream bed could take that load without the floodplain getting compacted completely. Like I said, at some of the sites where we tried to auger, we couldn't even push our steel auger through the floodplain. It was so hard. we need to retain those historic hydric soils in place on the floodplains wherever practical. I totally recognize that some of these restorations are happening in urban settings in very constrained spaces where the stream corridor is very limited, and the practitioners and the construction folks have to work in very limited conditions. So we do recognize those type of situations, but especially in rural or suburban landscapes or settings where you have the space, you should retain the hydric soils as is without excavation or without removal. For in terms of soil health, we should avoid commercial soil conditioners. We need to provide greater spatial variability in organic matter. When we are providing that on the floodplain, you need to increase the homogeneity, the heterogeneity, the other way around actually. You need to improve the spatial heterogeneity of organic matter. Don't create a uniform, homogeneous riverscape in terms of organic matter. We need to come up with specific soil tests, and that's what we're doing. Actually, Joe is going to be talking about in the next section here, pretty much the next slide onwards, about how we need to come up with specific soil tests. We need to target what are our desired endpoints for soil health? What bulk density should we be shooting for? What carbon content should we be shooting for in terms of the floodplain soil parameters? What denitrification rate should we be shooting for? What type of aggregation should we be shooting for? And okay, so what we are trying to do is compare our soils from the restoration sites to some of the more undisturbed soil locations where the soil health is excellent or very good, and see, hey, do we arrive at those endpoints for our restored sites? And if yes, how many years is it taking? And what would be the desirable endpoint for these soil health parameters? And finally, we want to also include these soil practices, these soil metrics, these soil endpoints in our restoration protocols, in our design protocols for floodplain restoration. And also make sure that the restoration agencies receive credit for protecting soil health. That's the way to do it. I don't think we need to regulate and force something down folks, the throat of folks doing this work, but bring them on, welcome them, bring them, make them a part of the solution. And so we need to incentivize. And this is where I'm going to stop and let Joe take over and present his part on some of the very specific experiments he's doing as a part of his research over here. So let me stop sharing it here and let Joe pick up where I left off.
Thank you, Shri. I'll be picking up from where Shri left off. I kind of have been looking into these best management practices for stream restoration and kind of including the floodplain into that design philosophy. Let's see if I can. Oh, there we go. Okay, so I am currently assessing the value and sensitivity of different soil metrics for pre and post floodplain restoration conditions of a chronosequence of sites. I have 12 sites going from 0 to almost 25 years post restoration. And this is part of 2 separate Chesapeake Bay Trust funded projects. Right now, our co-authors are looking at paper, which is pretty much finalized. That's soil metrics for long-term denitrification effectiveness. And our second paper is still in process and working on that one, but that's more soil metrics for long-term soil health. So we have our 12 sampled sites from across the Mid-Atlantic. Most of them are in Maryland, a couple in Virginia, and we sampled both the unrestored and restored sections of those floodplains. And we also, as part of the second Chesapeake Bay Trust project that's still ongoing, we've sampled 2 reference wetlands for kind of like a best case scenario where we find these desirable kind of like control metrics for soil conditions that are might not be fully achievable in this 25-year time frame we've kind of set for ourselves, but that's what we are shooting for. So the closer we can get to those ideal conditions, the better. So here's just a diagram of the 12 sampling sites. We have 3 from each age category. We have 0 to 2, 2 to 5, 5 to 10, and 10 to 22 years post restoration. And almost all these are in Maryland. We have 1 which is a difficult run in Virginia, but all throughout the Mid-Atlantic, all part of the Chesapeake Bay watershed, and pretty good geographic distribution for the size of the project that we're completing. Just kind of give you some ideas of what the sites look like pre and post restoration. We have one of our younger restorations here at Scotts Level Branch. This is a much more urban site, but you can actually still see remnants of that hydric pre-colonial wetland soil that Sri was talking about. And all of the restorations that we looked at were natural channel design, so that wasn't really taken into account. I don't believe that was that sediment was preserved, and in this area of Baltimore, the storm flow response is so flashy that really couldn't happen realistically. So there's some riprap in the restored section, but that's to protect the channel from the dramatic differences in flow. It's the median discharge is 1.7 cubic feet per second, but just in this past year, it's gotten to 500 cubic feet per second multiple times. And you can see all these plantings. So this is more of a urban design of natural channel design, but still appears to be effective. And we also have Howard's Branch, which was notable because it's one of our oldest sites at 22 years old, and it also incorporated a unique design. They had to take down some trees when they were completing this restoration, and they incorporated all that woody debris and wood chips into the restoration itself. So there's a big sink of organic carbon and organic matter at this specific restoration site, so that we kind of can tell that this site is performing differently than others, likely because of that consideration. We collected all the samples during the spring of 2023, 6 samples, 3 from each bank at the restored section, and 4 samples, 2 from each bank on the unrestored reaches. And we did a myriad of analyses for all these soil samples, including denitrification rate, bulk density, aggregation, texture, carbon and nitrogen analyses, denitrification rates. We also incorporated biological tests like PLFA, functional genes, microbial communities like NOS-Z, AOA, AOB. So a real large number of tests on these soil samples, so we could see what's really covariating with denitrification, what do a lot of the more successful restorations share in common. So took really broad approach to see what aspects should be used in future kind of goals for floodplain health. This is our conceptual model for our hypothesis of how we assumed these different factors would kind of progress over time. All the way on the left is our pre-restoration disconnected floodplain with an incised channel. When as soon as the restoration happens, we think that the bulk density is going to increase, along with our delta 15N and denitrification, just because we're disturbing all these different soils. We're compacting it, increasing the bulk density because of the heavy machinery. But after that kind of disturbance phase, a lot of these factors will improve with time. So bulk density, we think, will decrease. Soil moisture will increase because you're reconnecting that floodplain, and denitrification will kind of stabilize and increase. And organic carbon and organic matter will build up because of this new floodplain with hydrophytic foliage that likes being there. And here are some of our results. That it kind of follows our hypothesis mainly. We saw increasing trends for denitrification, organic matter, organic carbon, and soil moisture with time. So that's these green lines all increased with time, showing a successful recovery as these restorations age. We also saw bulk density increase as soon as restoration occurred, and then decrease over time to a level lower than that of the unrestored streams. And 15N followed that trajectory as well. And NH4, NO3, they kind of really didn't vary, at least not significantly. But that's kind of good to know that that might not be the best metric to use moving forward. Organic matter, organic carbon, bulk density, and moisture were all good metrics to assess the long-term changes in restored floodplains. They all showed significant differences using a NOVA test, and Tukey's honestly different significant tests. There was a strong correlation between denitrification rate and organic matter, organic carbon, and bulk density. And other biological and geochemical metrics are being assessed, including PLFA, NOS-Z, AOA, AOB. So we're going to incorporate all those into that second paper, where we're looking at the unrestored streams, the restored sections of those same streams, and then comparing those restored sections to our two pristine sites that have kind of ideal conditions that we're shooting for. Our manuscript draft is completed. Memories of the soil, evaluation of soil properties in bulk 15N to assess decadal changes in floodplain denitrification following restoration. The final print should be available this summer. It's in our final internal review. And our next manuscript is soil health changes and key metrics, which will try to further define what metrics should we be using to assess floodplain health post stream restoration, and what should these target figures be for things like bulk density, organic matter, organic carbon, and other factors. So the eventual goal is getting these soil health recommendations, revise floodplain restoration design protocols to include these, and try to help develop credits to incentivize these. There's, I'm sure as all you know, there's very little post-restoration monitoring going on at a lot of these restorations. I've been in a couple Chesapeake Bay Trust meetings, and that seems to be changing now. There's a lot of at least like 2 to 5 year plans for ongoing monitoring, but we're hoping to expand those and revise the protocols to benefit the environment and all stakeholders. We really could use your participation, scientists, practitioners, and regulators. So please contact us if you're interested in shaping floodplain science, practices, and policy at inamdar@udel.edu or jgalella@udel.edu. Or if you have sites that we can sample for soil health, we're always looking for more sites. So thank you for your time, and please let us know if you have any questions.
Great. Thank you, Joe. I'm going to go ahead and stop the recording.